going to talk about automatic parcellation of cortical surfaces using random forest. And thank you.
Okay, morning. Thank you for the introduction and sorry for the delay. My name is Meng. I'm a student in UNC Chapel Hill. Today I'm going to present a work. This work is about automatic parcellation of cortical surface using random forest. This is a work in ISBI lab in UNC Chapel Hill. First, I'll talk about the motivation. So, automatic and accurate parcellation of cortical surface into anatomically and functionally meaningful regions is very important in human brain studies. For example, in the study of the relationship between cortical surface and cortical structures and certain functions, or study the relationship between cortical regions and certain disease. The easiest way to do the parcellation is using the cycle-based parcellation method. So in this method, the boundaries are along the gyri, and this parcellation result can purely generated based on the geometric features. But unfortunately, the cortical regions may not have clear anatomical meanings. On the other hand, the anatomically meaningful regions may not the circle regions, and the boundary may not along the geometric features. Typically, usually this kind of parcellation are manually labeled, but manual labeling is very tedious and time-consuming. So people want to prefer using learning-based method to do the parcellation. So in learning-based method, they will not only use geometric features, but also use prior parcellation information. The prior parcellation information are usually manually labeled anatomically meaningful regions. For example, free surfer belongs to this kind of method. And because free surfer only use very limited, very simple geometric features, so the performance is very limited. Recently, people use random forest with highlight features to do brain image segmentation and achieve very high performance and high accuracy. The reason is that highlight features can provide a rich neighboring or context information, and random forest can learn an optimal utilization of this kind of information. So we want to use this technique to do the parcellation, but it is not easy. It's not straightforward because the definition of highlight features in 3D in image space cannot be directly applied to the cortical surface, and also because random forest classify each vertex independently, so the output may be not spatially consistent. To solve these problems, in this paper we propose a method to compute highlight features on the cortical surface, and also a method using random forest with auto-context features and geometric features to do the parcellation. Finally, we propose a refinement method using graph cut to get a spatially smooth, spatially consistent surface parcellation. This is the pipeline of our method. So in the training stage, we can see using the training data, we first train a set of random forest, and in the testing stage, given the testing data, we first use we will use the forest to classify each vertex on the cortical surface. So for each vertex, we will have a probability distribution suggest us which cortical region the vertex belongs to. Next, we'll use graph cut to refine this result and get the final result. Next, I will talk about how to compute highlight features. So it is very difficult to directly define highlight features on the original cortical surface. So we map the information from the original cortical surface to the spherical surface. So in this work, we use the convexity and mean curvature. We can also map the label information to the spherical surface. And next, we can compute or we can define the highlight features on the spherical surface. The highlight features can be computed on each vertex on the spherical surface. And when we compute the highlight features, we only consider a neighborhood of the given vertex. So in this table shows four types of highlight features. Each circle stands for a neighborhood of a given vertex. And we cut the neighborhood into black regions and white regions. The highlight features can be computed using the equation above. And in this equation, the character M stands for the mean curvature or the convexity. For example, if M stands for the convexity, the highlight feature is equal to the sum of the convexity in the white region minus the sum of the convexity in the black region. Also, use different rotation and different size of neighborhood. The highlight features could be different. So in this work, we use different rotations and scanning of neighborhood to generate a number of highlight features. Intuitively, the feature A and feature C will detect the boundaries, and feature B will detect the volume or the reach. The feature D will detect the corners. Next, I will introduce how to use random forest with auto-context to do the parcellation. So in the training stage, given the training sample will have three information: the position information, the attributes, and the label. The attributes are usually in this application. The attributes are the mean curvature or the convexity. So we first compute the highlight features from the attributes, and then use the position information, highlight features as input features, and label information as our classification target to train the first forest. Next, we can apply the forest to the training data and get a probability maps, a set of probability maps. This probability map, each probability map is corresponding to a region. Next, we can compute the context features from the probability maps. The context features are also the highlight features. The highlight features computed from the probability maps. Next, we can combine the context features with the old features together to train a new classifier. And of course, we can get a new probability map. So this process can be repeated several times. And finally, we can have K random forest. The testing stage is very similar. So we have already had K random forest, given the testing data with position information and attributes. First, we compute the highlight features and use the random forest 1 to generate the initial probability maps. Next, we compute the context features and use forest 2 to update the probability maps. So similarly, we can continue to update it until we get the final probability maps. So as I just introduced, using because random forest will classify each vertex independently, so the output is spatially inconsistent. But using random forest, this result can be refined. However, if you look at some local areas, you can still find some regions like this. The spatial inconsistency still exists. So we want to further refine this result, and we use GraphCAD. Remember, right now, for each vertex, we have already had the probability distribution, and we treat this probability distribution as Markov random field, and the GraphCAD will try to minimize the energy of this field. We want to minimize this energy function. So this function has two terms. The first term is date fitting term. The next term is spatial smoothness term. The date fitting term is computed using this equation. The Pxy stands for the probability of the vertex x belonging to region L. So this probability is the output of random forest. So we can see the date fitting term means we want to make the final result as close as the output of random forest. The smoothness term is computed using this equation, and Nx means a set of neighboring vertex pairs. Cx is a cost function. The range of this cost function is from 0 to 1. Here, dirt is a penalty indicator. For example, if we have two neighboring vertices and these two neighboring vertices have the same label, that means they are locally smooth. So the penalty is 0. But if they have a different label, we may put some penalty on this. But how much the penalty is depends on the location of the vertex on the cortical surface. Intuitively, so when humans do the parcellation, they will tend to cut the cortical surface along the banded place, but not along the flat place. So we want to put a large penalty on the banded place and large penalty on the flat place, but small penalty on the banded place. We're doing this by consider the normal directions and the curvatures. Here, nx and ny are the normal directions, and hx, hy are the mean curvatures. So in the flat place, the normal difference will be very small, and the curvature will be very small. So this cost function will return a large value. But in the banded place, the mean curvature is small, and the difference of normal is very large, so it will return a very small value. We test our method on the dynamic dataset. In this dataset, there are 39 adult brain MR images, and the cortical surface were reconstructed by free surfer. On each cortical surface, we have 35 gyro-based regions. Okay, here are some results. The first row shows the ground truth. The second row shows the results of our proposed method. For a better inspection, we map the label information to the inflated cortical surface. And you can see the random forest will have a very rough result. And auto context can refine this result. GraphCut can further refine this result. Now this figure shows the depth ratio in each cortical region. And the second figure shows the improvement using auto context. The third figure shows the improvement using GraphCut. So finally, we compared our method with the previous studies, free surfer and spatial demos. We computed the depth ratio in each cortical region. And in this set, we can see our method outperforms the other two methods, especially in the small region, for example, the region 7 or region 27 or region 65. Okay, here comes the conclusion. We proposed the method to compute the highlight features, and we also proposed the method using auto context together with the random forest to do the parcellation. And finally, we use GraphCut to refine the result to get, especially to refine the boundary areas to get the final result. Thank you for your attention.
Thank you for the talk. I have two related questions. Could you please go to the slides where you show the auto context framework? Yes, the question is first, could you please elaborate the reason you want to do that iteratively, basically do that multiple times, and what is the advantage of doing this? The second is, when do you decide how many times you want to do that?
Okay. The question was why we want to do this iteratively, and the second question is how many times we do the iteration. So in my implementation, I only use 3 iterations. And the reason why I use iteration is, at the very beginning, the output is very rough. And you can see, as I just mentioned, the random forest will only classify the vertex independently. So there is no relationship, or they didn't consider the situation jointly. So for 2 neighboring vertex, maybe they should have the similar probability maps or should have similar label, but random forest may give them very different label. But using auto context, it will give you a large information about the neighbor information. For example, it will tell you in a neighborhood what's the mean information, or what's the difference between two neighboring vertex. Combine this information together, so the random forest can. So with this kind of information, the vertex are not independent. When you assign a label to a vertex, it will not only consider the local geometry information, but it will also consider the label of the other neighboring vertex and try to give them similar labels. So that makes the output much smooth.
I agree with that. Then why do you decide 3 times instead of 5 or 6?
Okay, the question is why I choose 3 times. You can see in each iteration we will have some improvement, but with the iteration goes on, the improvement will become small and small. So typically in the first iteration, you can see the improvement is very large, but after 3 iterations, the improvement is very small. So I just saw that.
I agree. Basically, we converge, but actually, there is no specific threshold or delta sign indicator to say, okay, it's a stop, it's optimized. But you just decide based on your experience or something like that.
Yes.
Thank you.
In the interest of time, I think we should